Hi there. My name is David Weitz, and in this talk, based on joint work with Seffi, Nitya, Abhishek, Aravind, and Renata, I'll tell you about hypersimplex correlated sampling and new dimension-free bounds for this problem. By the end of this talk, you should know what this type of sampling even is, how we get our dimension-free bounds for this problem, and hopefully make you think about whether this type of algorithmic primitive is useful for your own research. And with that, let's dive in. So consider possibly the most basic algorithmic or randomized algorithmic primitive, which is sampling from a discrete distribution. So here, what we have is a vector in the probability simplex. So these are all non-negative coordinates summing up to 1. Here we have an image of the probability simplex for 3 coordinates. And what we'd like to do is sample from this distribution. So we'd like to sample a single element, set S of size 1, subset of the integers 1 through n. And we'd like to do so in a way that gives each element exactly the probability that this vector prescribes it. So the probability that element I is sampled is xi. We all know how to do this. Let's add a twist to this, which is correlated sampling. Here, what we'd like to do is sample from multiple vectors, multiple distributions, possibly given to us in the future, so we have to prepare in advance, in a way that maximizes the overlap. And these types of questions have been studied by statisticians for over 70 years now, motivated by the desire to minimize the training time to train people surveyed for different surveys. We'll talk about some TCS applications shortly, but let's concretize this type of question. So again, instead of sampling a single vector, we'd like to initialize an algorithm with some random seed so that for any vectors in the probability simplex, again, we sample in the way that we had before. We sample a single element for each vector x. Each element belongs to the set S for x with probability exactly xi. And moreover, for any pair of vectors, we want the expected symmetric difference between these vectors to not be much greater than the L1 distance between the input vectors. Okay, in particular, it should be at most alpha times this L1 distance. Okay, and we'll refer to this alpha as the stretch of the algorithm. Okay, so in particular, if x and y are exactly the same vector, you should output exactly the same thing, more generally. Okay, so this type of problem appears in a large number of applications in theoretical computer science. I'll mention a few here. So this has found applications in approximation algorithms. Min hashing is a special case of this in locality-sensitive hashing, parallel repetition, cryptography, parallel sampling, replicability and privacy in machine learning, and the list goes on. Okay, so this seems like a very, very useful algorithmic primitive, and what we study in this work is the following generalization of this problem to hypersimplex correlated sampling. So now instead of sampling a single element, we'll sample k elements. So we are given elements in the nk hypersimplex. So this is the slice of weight k in the n-dimensional hypercube. So again, non-negative vectors within the hypercube, but the sum of the coordinates is exactly 1. So here we see delta 3, 1, that's the probability simplex. You could also consider delta 3, 2. So here we sample exactly 2 elements. And again, we want to sample a set of size exactly k, hit the marginals for every element, and moreover, if x and y are close, then we want the symmetric difference between the set for x and the set for y to be somewhat close. Okay, so for some small stretch alpha. So let's actually try and quantify things here. So what's known? So for k equals 1, the ratio of 2, so the best stretch possible is 2, and so this has been known for over 2 decades now, and it's also known to be optimal. For k greater than 1, even k equals 2, unfortunately, our understanding is a little more rudimentary, and a result of Chen et al. From iCalc almost a decade ago shows that you can get logarithmic stretch in the input dimension. Okay, so even if k equals 2, all we know is a log n type guarantee. And what we show in this work is that this dependence on the dimension is not necessary. And instead of getting bound that is logarithmic in the dimension, you can get something that's logarithmic in kind of a target dimension in subsets. Nonetheless, we call this dimension-free bound. So we're about 5 minutes into this recording. If you're only interested in the high-level bit, you can skip to the end of the recording and get a sense of what are our complementary results and think a bit more about the more general problem that we study in this work. If you're interested in a little more about the techniques, then let's start with a quick observation before we dive in. And the quick observation that we'll use throughout is this observation made by Chen et al., which is if we just break up the difference between y and x into just kind of following a walk along, the grid, kind of following the Manhattan distance, and using the fact that the symmetric difference is a metric and therefore satisfies the triangle inequality, you can assume without loss of generality that the vectors that you're interested in, y and x, are just only differ in a single coordinate. Okay, so they're exactly the same except for one coordinate where y is x plus an epsilon or minus an epsilon. Now, the way I describe this here, they should have exactly value k, but the more general problem we study has this equality be an inequality, ditto for this one. Okay, so what's our general idea? We're starting off with this dimension-dependent stretch, and what we'd like to do is to get to a dimension-independent stretch. So what we're going to do is try and project the large dimension into a smaller dimension and apply the dimension-dependent bound there. So let's try and illustrate this with some figures repurposed from a talk on bin packing. So our input here is an n-dimensional vector, and the sum of the x's is at most k. So I'll denote the non-zero values by these colorful boxes here on the right. And I'll have k bins in the bottom, where using some, say, random hash function, I'm going to map the coordinates of the original vector into this new vector. Okay, so let's remove these numbers over here. And what we have is we'll just hash these coordinates however. And the new vector that we get, this k-dimensional vector, will just have, for every bin b, the sum of the x values hashed into it will be the new value of this coordinate in the new vector x hat. Okay, and before we go into how exactly we leverage this, right? Intuitively, what we'd like to do is somehow now run the dimension-dependent algorithm in this lower dimension and somehow inverse this projection. Invert this projection. Okay, so a quick observation is that since the sum of the x's was at most k and we're hashing into k coordinates, for every one of these k coordinates or bins, the expected x value hashed into it is at most 1. What we're going to do as a quick kind of thought experiment is assume we have some kind of magical hash function that not only guarantees this inequality in expectation, but actually guarantees it deterministically for every coordinate, okay, for every bin. Okay, so all of these bins here are of size 1. So for example, this hash function will not allow us to move this, will not set this purple item with the blue item and the red item, right? This is a no-go. Okay, so this is our assumption here. So let's start and get a sense of what this algorithm would look like if this assumption actually held. If we had this magical hash function that guarantees what we know should hold in expectation, but guarantees it deterministically for each coordinate. Okay, so step number one, project. Okay, so we take our vector x, use this magical hash function h, and get a new vector x hat with all of its coordinates between 0 and 1. This is the assumption. It's a k-dimensional vector, and the bth entry of this vector is exactly the x value that's hashed into this bin. So I'll use capital B to denote the pre-image of bin B. So all the coordinates that are hashed into this bin. Okay, now what we're going to do is use the dimension-dependent algorithm to get from this vector x hat a set Sx hat. Okay, while getting a log k stretch. And finally, we want to kind of lift this projected set back into n dimensions. And what we're going to do is for each sampled bin, so each bin B that is in the set Sx hat, we run the algorithm for k equals 1 and add item I with probability xi over x of b to the output set Sx. Good. So what do we get here? Assuming a hash function as above, so which guarantees that all the coordinates of x hat are between 0 and 1, my claim is that the above is a log k stretch algorithm. Okay, and to see this, we're just going to go through the three properties of hypersimplex correlated sampling algorithm. So first, for cardinality, the set Sx has size exactly Sx hat, right? So for every sampled bin, we'll sample exactly one item. And the set Sx hat sampled has size exactly k by the properties of the hypersimplex correlated sampling algorithm that we use in step 2. And what about the marginals? Well, what's the probability that we output element I? Well, first we need to sample its bin, and then we need to sample that element. So the probability of sampling the bin is exactly the x value of elements associated with it. And the probability that we sampled I conditioned on its bin being sampled is xi over x of the bin. Things cancel out nicely, and we get that every element I is sampled with probability exactly xi. Finally, what about the expected symmetric difference? Well, sets Sx and Sy differ by 1 for every difference between Sx hat and Sy hat. So every bin that's sampled in x hat for x hat and not for y hat, and vice versa, results in an element sampled for x and not for y, and vice versa. And moreover, for the single coordinate where y and x differ, remember y is x plus epsilon times a unit vector. For that single coordinate, we incur an extra additional, maybe +2 term for the symmetric difference with probability proportional to epsilon. So proportional to the L1 distance within that bucket, within that bin. Okay, and from here on out, what do we have here? So this is log k times the L1 distance of x hat and y hat, plus this order 1 times epsilon term. Again, y hat and x hat differ in exactly a single coordinate by a value of epsilon. And so what we get overall is a log k times epsilon, or log k times x minus y in L1 distance. Great. So again, what we get is a set of size k, we hit the marginals, and we get a stretch of log k. Okay, so we started with the assumption of a particularly strong hash function. Let's remove this assumption by performing the following modification to the algorithm. If a bin is overfull, we just fall back to the kind of quote-unquote naive dimension-based algorithm, so a log n stretch algorithm. Now, this should happen infrequently, otherwise our expected stretch overall will be high. So what we're going to do is we'll try and guarantee that this is unlikely. That'll be the kind of the gist of most of what we're going to see soon. And for that, we'll use a slightly larger target dimension. Instead of hashing to dimension k, we'll hash to some dimension d, which is some poly k in log n. So maybe say k to the fourth log n to the fourth. Okay, so we've removed first assumption. Let's replace that with another assumption to kind of make the analysis a little easier, just to kind of get a sense of things first. So let's suppose that every coordinate has fairly small value, let's say at most 1/8. Then, under this assumption, what we'll find is that the probability that there exists a bin that is overfull is polynomially small in the input parameters. In particular, it's at most 1 over d. Okay, so how do we show this? We'll just break things down into small and medium-sized items. So small items are, or small coordinates, are all the coordinates hashed into bin B, such that their x values at most, say, 1 over log d. And what we'll show is that the contribution to xb of small items and of large items should not be too high with decent probability. In particular, since these x values are so small, by Chernoff bound, what we can show is that the contribution of the small items to x of this bin, the probability that this is greater than 1/2 is exponentially small in 1 over this term. So exponentially small in log d, and for the appropriate hidden constant, what this gives us is something that is polynomially small in d, say at most 1 over d squared. What about the larger items? Well, the larger items are still at most 1 over 8. They're at most 1 over 8 and at least 1 over log d. So there's maybe k log d of these, and to exceed 1/2, you need at least 4 of these. So by union bounding over 4 tuples in items hashed to bin B that are not too small, the probability that this set of elements contributes to the x value of the bin at least 1/2 is the probability that some 4 tuple is hashed to the same coordinate, which happens with probability d cubed, right? So you fix the first one, and then the other 3 need to be hashed to the same location. We pick d to be at least this term, so what we get is this is at most d over d cubed, or in other words, at most 1 over d squared. Great. Finally, union bounding over all d coordinates, what we get is that the probability that xs is at least 1 is order 1 over d. What do we get from this? Well, under this assumption too, that all the items are small, or at least not too large, the expected contribution to the stretch, so symmetric difference over the distance between x and y, times 1 if the bins are overfull for both x and y, is order 1. Okay, so the expected contribution to the stretch of scenarios where some bins are overfull is only a constant. So let's try and put these things together. So far, under assumption 2, what we have is that in the quote-unquote good scenario, where no bins are overfull for x and y, this contributes to the expected stretch, something logarithmic in the dimension. And remember, the dimension here is something polynomial in k and log n, so this is a log k plus log n term. So this is almost what we'd like to get. On the other hand, the contribution to the expected stretch of the scenario that bins are overfull for x and y is only a constant. So at this point, it seems like we're almost there, but unfortunately, we ignored one important case, which is the case that some bin is overfull for y, but none are overfull for x. And this, as the title of this slide suggests, I claim is a catastrophic event for us. And here's why. If we denote by C for catastrophic, the event that there is some bin, or there are some bins that are overfull for y, but none are overfull for x, then what happens is that we end up running the simple algorithm for y and the smaller dimensional algorithm for x. In other words, we run two different algorithms that at least I don't see any way of correlating. So the only thing that we really know here is that for x, we output a set Sx of size k, and the same for y. And so the symmetric difference between these guys is at most 2k, and the contribution to the stretch, or let's say the conditional stretch conditioned on C, it could be as high as 2k over the L1 distance of x and y. Okay, remember that this term could be some tiny epsilon, so this is really huge. Okay, so what we need to do in order to offset this is make sure that the probability of this catastrophic event is inversely proportional to this conditional stretch. So how do we do this? Some animation broke here. I hope you'll bear with me. So again, what we want to guarantee is that the probability that the bins are overfull for y, but none are overfull for x, is proportional to their L1 distance over k. And to do this, we'll redefine the notion of being overfull to mean that the x value hashed into this bin is at least 1/2 plus tau for tau some uniform, say 0 to 1/2 term. Okay, so how does this help us? So again, we'll have x and y, where y differs from x by only one coordinate. And let B be my favorite items bucket. So this different items bucket. Then, in order for a bin to be overfull for y but not for x, the only bin that could be overfull for y, if none is overfull for x, is this bin B. I guess lowercase b. So what we need, this bad event over here, is precisely what I have here. So I need the x value of bin B to be less than 1/2 plus tau, while the yb is greater than 1/2 plus tau. Another way of putting this is I need the probability, I'm trying to bound the probability that yb is greater than 1/2, and the threshold falls somewhere between xb minus 1/2 and yb minus 1/2. Now this, by an argument similar to what we showed in the previous slide, is something like order 1 over d. And this term over here, which is independent of the above, since tau is just some independent uniform variable, is the probability that tau, which has measure, which is basically drawn from an interval of length 1/2, lands in some segment of length at most epsilon. Okay, so this happens with probability epsilon over 1/2. All in all, this is order epsilon over d, and since d is at least k, it's even at least poly k, this is order epsilon over k, which will wash out, which is exactly what we wanted to show. And so summarizing what we had on this slide and the previous one, under assumption 2, the expected contribution to the stretch of this catastrophic event is again just a benign constant. Okay, so let's wrap up this warm-up. So far, under the assumption that no items are too large, the expected contribution to the stretch of the scenario that no bins are overfull for either x or y is order log d. The expected contribution of the scenario that bins are overfull for both x and y is a constant, and the expected contribution for the scenario that a bin is overfull for y but none overfull for x is again just a constant. So all in all, under assumption 2, just by linearity of expectation, the expected stretch is logarithmic in d, and by a choice of d, this is logarithmic in k plus doubly logarithmic in n. Okay, so before we get to the promised log k bound, let's briefly mention how we remove this assumption that all items are small, or not too large. What we do is just employ a two-level hashing scheme. So we hash the not too large items into bins as before, into d bins as before. And now we'll also hash both bins and large items, so where the xi is at least 1/8, into slightly larger dimensions, say d cubed. And again, we'll run a log n stretch algorithm in case of some problematic collisions in this case. Okay, collisions between different bins, or between different large items, or between a bin and a large item. And note that intuitively this is not a big deal if for both x and y we have a collision, because the probability that this happens is fairly unlikely. By taking union bound over all pairs of large items, there's 8k large items. Their size at least 1 over 8, and the sum of all the coordinates is most k, plus the d coordinates for the medium-sized items that were hashed into bins. If you union bound over all pairs of these, the probability that they fall in the same bin, so 1 over d cubed, all of this comes out to an order 1 over d. Okay, so this is kind of similar to our analysis for the simpler single level hashing scheme, where we said the probability of a bin being overfull is order 1 over d. Now, actually accounting for these large versus small items and having a different behavior for large and small items, again, introduces a bit of tension between the runs for x and y. And in particular, it could be that coordinate I could be large for y, but not for x. And again, we might run different algorithms for x and y. And the way to overcome this is similar to the way we overcame the issue of a bin being overfull for y but not for x. Just add a uniform random threshold on top of that. So we'll say a coordinate is large if it's above some uniformly random threshold, say 1 over 10 plus 1 over 10 or something. Or I guess plus uniform 0, 0 to 1 over 10. Okay, so the analysis is similar to what we saw in the previous slide, so I'll skip the details. You're welcome to read the paper. But what we get from this at the end of the day is the same log d, which is log k plus log n stretch. Now, if you remember at the beginning of the talk, I promised you a clean log k stretch, so we're an additive log n away from that. But if you notice, there's really no reason for us to stop here. And in particular, we could just recurse this construction. So the algorithm I kind of highlighted in the last few slides decreases a stretch of alpha if you use dimension d, which is poly k in log n. So here this is alpha equals log n, but generally this would be poly k in alpha. So we went from a stretch of log n to logarithmic in k and the same log n. So log k plus log n. No reason to stop here. Okay, so generally what we get is using an algorithm with stretch A and taking a target dimension d to be poly k in alpha. What we can get is from a log k plus log n, we can get to log k plus log n. From a log k plus log n, we can get to log k plus log n. I think I miscounted here. I'll stop trying to do my impersonation of a turkey by saying log way too many times, and just point out that if I repeat this, say log star many levels, what we end up bottoming out at is a stretch of log k, as promised. And with that, let's summarize. Our main result is the following. For any input dimension n and target dimension k, there exists a hypersimplex correlated sampling algorithm with stretch that is just logarithmic in k and independent of n. Complementary results, which I maybe kind of hinted at here, there's still some more details on top. This algorithm can be implemented efficiently, and in particular, ignoring the log star n from the number of levels of recursion, this algorithm just requires you to read the number of non-zero entries of this vector. So if you have access just to a list of the non-zero entries of x, this will take you only essentially something linear in that term. Similarly, you can implement this algorithm in almost logarithmic parallel depth or dynamic update time. So this algorithm is pretty fast for any model you might be interested in, I imagine. So this might be useful. Speaking of this algorithm being useful, we also highlight three simple applications, none particularly groundbreaking, but give a sense that this might have some broad applications. So the first application is a log squared k competitive online paging or online caching algorithm. This is quadratically worse than the state of the art, and but this does give a sense that this is a nice algorithm for online settings. Another application we get is a log k approximate multi-label metric labeling algorithm, improving a result of Chen et al., which was one of their motivations for studying hypersimplex correlated rounding, correlated sampling. And finally, we give a bicriteria approximation algorithm. I won't even tell you exactly what the parameters are, but for swift dynamic submodular reallocation, which is a problem which admittedly we kind of cooked up here to illustrate that our algorithm also preserves submodular objectives. So if you like thinking about submodular maximization, this might be a useful tool for you too. Finally, let me again reiterate what I mentioned kind of early on in the talk, which is that we can do a little bit better than the hypersimplex. We can deal with the convex hull of the origin in the hypersimplex. So now the sum of coordinates is not exactly equal to k, it's at most k. We can output a set whose size for any input vector x is essentially the L1 norm of x up to floors and inevitable floors and ceilings. You hit the marginals, and the stretch is at most logarithmic in the initial distance. Two natural questions suggest themselves. The first, log k is an improvement on the previous bound, but we don't have a good sense of whether or not this is necessary. Can you improve this log k term, or can you rule out any improvement on this? Can you get a constant? Can you show that you must incur some slowly growing and k function? Still up for grabs. And beyond this, as I alluded to earlier in the talk, correlated sampling for the probability simplex has had an inordinate number of applications in theoretical computer science. Can we find further applications of our fast hypersimplex correlated sampling algorithms or subsequent ones beyond the applications we illustrated in this work? Something to think about. Thank you for your time.